Today we are going to be looking at types of spectrum. I will remind you that in the previous lesson we talked about the spectrum of electromagnetic radiation. We also looked at how visible light works. And I'll remind you that in this case, the colors in this spectrum are distributed from red toward violet. In this case, in this spectrum, the boundaries between each color do not exist. This kind of spectrum is called a solid spectrum. But when we talk to you about the hydrogen atom, we will find out that spectra come in other kinds. For example, it depends on what kind of spectrum we want to get. Either we get an absorption spectrum or we get an emission spectrum. In this case, we need to understand what is going on in each of these examples. If we're talking about an absorption spectrum, in this case, for example, an electron that is at level 3 can go to level 2. Thus, it appears to descend from the upper levels towards the lower levels. Such a transition occurs by absorbing quanta of light. In this case, if we want to get such a spectrum, it will require the expenditure of this quantum of light. And observed in this case, this transition is only observed in the Lyman series. If we talk about the emission spectrum, in this case, the transition is the other way around. When from the lower level, let's say level 2, the electron goes to level 3. In this case, there is emission of quanta of light, and in this connection, all the lines of the spectrum, all the lines of the series from Lyman, Paschen, and so on will be observed. Thus, there is a general formula. If we want to calculate what the quanta of light will be, that is Hn, we can calculate by taking away from E2 minus E1. The only thing is, in one case it will be a minus sign, in the other case it will be a plus sign. Now let's see how this happens in hydrogen. Let's see. The first spectrum you see is a spectrum, which is called the absorption spectrum. It represents actually an overlay on the visible light spectrum, and in it the lines that you see here are clearly visible. There are 4 of these lines. They're superimposed in a certain way. This is because this is the way the electrons in the hydrogen atom move. Now notice that this spectrum is discontinuous. It has clear separations and lines are visible. Therefore, such a spectrum is no longer called a solid spectrum. Now let's see what the spectrum and emission looks like for hydrogen. You can see the same lines, only they are arranged conventionally, it turns out, on a black background. And these lines look like colored lines, which are visible here. And hydrogen has 4 such lines in this emission spectrum. It turns out that there is a red line, there is a blue line, there is a violet line, and there is a green line. That's exactly how many of these lines hydrogen has. But if we were to take, for example, atoms of other chemical elements, they would have a different kind of spectrum. They would probably have more lines. And then each of the lines allows us to identify this chemical element. Between the 2 of them, when you take the absorption spectrum of absorption and then you compare it to the crushed spectrum, you can identify that chemical element. What this spectral analysis is good for is for you to be able to identify exactly what chemical element it is. Once again, you see spectra for the hydrogen atom, the very first chemical element. What allows us to determine such spectra? For example, we can do a spectral analysis in outer space, let's say on some of the planets or on the sun, including, for example. And you can identify in this connection the elements that are on these space bodies. It turns out that you may not be there, but nevertheless you can determine what chemical elements are there. This is the way, I would like to say, that the element helium was discovered in the sun in the beginning, and the same spectra were obtained. They compared it and found out that there is an unknown element there in the sun, which according to the spectra, which were obtained on the Earth, was not in the beginning. That's why helium is called solar helium. And then it was found on our planet For every chemical element, their emission and absorption spectra serve as a sort of business card, enabling the identification of the element. However, it should be noted that emission and absorption spectra have broader applications beyond chemical element identification, but also to identify what kind of substances they are. The only difference is that, for example, absorption spectra are usually used at low pressure, and in this connection, the temperature, for example, of this process can be low. But for the spectrum to get emission, accordingly you need temperature. And then the particles are accelerated, and you can determine the spectrum for this chemical element just by this kind of spectra. In other words, these two spectra are then necessarily compared to each other. There is a map of spectra by which certain substances, certain chemical elements are analyzed. You can see such maps, for example, on the internet, in order to see, for example, how such spectra differ not only for hydrogen, but also, for example, for iron, sodium, or potassium, as well as for other chemical elements. I think it's worth looking at. Goodbye.